So this does not belong to the lecture, it's only for an exercise, because we're waiting. I will start doing the lecture on Fourier series and I start at 9, waiting for the other students. Yeah, I think they forgot that we started at 8:30. Yeah, so it's better for them, because we're going to do the Fourier transform method. But they are there at the beginning because else they miss essential parts. Yeah. Okay, so about the exercise. And I gave it to part 2, yeah. So this is the essential exercise. So we want to have the Green's function and we have a Robin condition. K is not equal to 0. For K is equal to 0, you can do it immediately. You take here a source, over there a source with the same sign, and you have the Green's function. Now in this case, so on the boundary you have this. And then the hint will be, or I give only a hint. Introduce Vxy is equal to introduce a new function v which is equal to the g dy plus kg. And then derive the problem for v. And then try to solve the problem for v. And if you have v, yeah, if you solve the problem for v, then you can determine from this PDE, if you know v, you can determine g. Yeah, and you will see that if you do this transformation, then on the boundary, v will be 0. That's a zero-time condition, so you know how to construct for such a problem. The only question now is, what equation does v satisfy? Yeah, but that's just gy plus kg. Yeah, if you figure out what equation that is, that's again a Laplace equation. But there's a trade-off now, so I can give you now a more difficult exercise. So then the third part of the exercise now will be consider the region, the domain. So what I then give you as additional exercise is the following. Now we restrict the domain to the quarter plane. And on the boundaries, you have again Robin condition, the same Robin condition. And now I would like to determine again G. So I replaced, give you a hint here, but then I introduced for you a new problem. Yeah? And then if you look carefully, then what I'm now asking you is we did this problem for Dirichlet conditions, we did this problem for Neumann conditions, and I now also let you do it for Robin conditions. Yeah, and we did this, and we also did it over here. It turns out that if you have such a condition, you cannot have that simple extension with a reflection point. Now you get something more complicated. Also think about it. If you are looking at the method of separation of variables and you are using Fourier series, then if you have simple boundary conditions like Dirichlet and Neumann, you always look at a nice simple cosine series or sine series. And you can explicitly determine the eigenvalues. Lambda is n pi over L squared. Yeah? But if you have Robin conditions, you get a transcendental equation. The tangent of lambda is equal to 1 over lambda or something like that. So you can never compute exactly what your lambdas are. Yeah, and that's more or less also happening here. There's something happening more complicated. So this completes the whole story because I did this problem for Dirichlet, Neumann, and now also for Robin conditions. But if you look in the books, this problem with Robin conditions you cannot find. Similarly, that problem. And the same thing for the circle. And those solutions are usually not given. Yeah? Okay, so these are the hints. And try to work it out. These are difficult, but that's the... Here there's an extra complication. Because you have two boundaries. Actually, if you have two boundaries and you do that transformation, then you spoil the other boundary condition. You have to think about how to tackle that. We just wait another 5 to 10 minutes for the other students because we thought that some of them forgot that we started at 8:30. Yeah? Okay, so we have still 5 minutes, 10 minutes break. This is usually the problem that you want to solve. Yeah, and then you are looking for the function due, well, is and then you get this, so you get a new PDE for V, which is actually almost the same as the original one. And then V is 0 on the boundary. And then you have to look for the Green's function for this problem. And you can easily do that. And so that means that you can easily solve the problem for V. And that's then you go back, so if you know V, then you can also determine U. So this is usually the original problem, which you would like to solve. Now for a function u, and then you have this transformation, and then you get Laplace v is a new function f, and then v0 the boundary, and you know how to solve that. So you know v, and this is a first order PDE. And those of you that followed the course in Palembang, we also explained how to solve first order PDEs with the method of characteristics. So we can solve that problem straightforwardly. But that's the reason why I gave this a difficult exercise, because you have also to solve the first order PDE, and I don't know whether all the students know how to solve it. Yeah, but you and Ditya and Eric and Erika and Koos, they should be able to solve it. It's perhaps also interesting to tell you that I have a colleague, and I discussed this problem recently with him, that we found how to tackle this problem. And he's also teaching the course of partial differential equations, and he told me that he was glad that he never had a student that asked him how to solve this problem. And with one of my PhD students, my former PhD students, who's now also a lecturer in a university in the Netherlands, we plan to write a paper on this. So it's quite close to research. But it's, if you look at it, the solution technique again, if you find it, it's quite elementary. Yeah? So, I can explain it to you. Okay. Shall we start with the lecture? Yeah. Can I wipe this out? Yeah. Yes. Today I would like to start with the Fourier transform method. And I first will explain you the idea behind those methods. Then I will go back to Fourier series that you know. And then I will give you an idea how the Fourier series, how from those series you can derive at the Fourier transform. Yeah, but you can also look from a mathematical point of view. I can immediately give you the definition, this is the Fourier transform. Yeah, but I always like to show you where it's coming from, so that you get an idea why you are defining the Fourier transform in this way. Yeah, so I tell you something about its origin. Then, what I'm going to do is I'm going to determine from a lot of functions, I'm going to determine the Fourier transform. Yeah, and those who already worked with transform methods, usually in a certain domain the problem is too difficult to solve. You apply a transformation, and in that transform domain, the problem is solvable. And then you have to apply the inverse transform to go back to the solution in the original domain. And to do that, usually you have to do an integration in a complex plane. So you have to know something about complex function theory. Yeah, that's the reason why also a lot of students, when they become PhD students, they're always checked on the points, did you do PDEs, did you do nonlinear differential equations, did you do complex function theory, did you do something on numerical methods? Yeah? So those courses you have to do. But since I assume that there are still a lot of bachelor students also in the group, so what I'm going to do, I'm not going to talk about the inverse of the Fourier transform in complex plane, but I just will make a table. So I will take a function and then look what is the function in the other domain. And then I make a table, and with that table we can solve also lots of problems. Yeah? So that's the whole idea, and I will do that today and tomorrow. And why are we doing that? Because up to now we only looked at problems that were depending on x space variable, or x and y, or x, y and z. And they were not depending on time t. To solve time-dependent problems, like the heat equation, like the wave equation, we will need to use the Fourier transform. Yeah, so there is a reason why we are now introducing the Fourier transform. To construct Green's functions more easily, we have to use the Fourier transform method to solve those problems if we want to see what the Green's function looks like for a time-dependent problem. Yeah, up to now, they were all only depending on the space variables. Okay, the Fourier transform. What is the idea? Well, you might have an initial value problem, or an initial boundary value problem, doesn't matter. And usually the coordinates that you're having are x variables and t variables. So space and time. Yeah, you have an initial value problem, you have or an initial boundary value problem. Yeah, think of the PDEs that you have, a weight equation, a heat equation, whatever problem. Usually it's too difficult to solve it in this domain. So what people are going to do is they are going to use a transform method. And one of them is the Fourier transform method, or some of you already know the Laplace transform method for ODEs. Yeah? Also, bachelor students know something about the Laplace transform method? Yeah? The Laplace transform method? Laplace transform. You didn't get it? Okay. Okay, but some students, when they follow a course on ordinary differential equations, will also get at the end the Laplace transform method. Yeah? But if you have not seen it, also not a problem. Yeah? If I have time enough next week, I will also tell you something about the Laplace transform. Because the Laplace transform actually is a special case of the Fourier transform. Yeah? But a lot of people in elementary courses of ordinary differential equations, they already have seen something on the Laplace transform method. But okay, the idea. If you apply that, so you have here a problem, you will get a problem. If you apply the Fourier transform method, you will usually get a problem in omega and t. So that's a space. Transformation. So if you apply the Fourier transform, or if you apply the Laplace transform, usually you will get a problem in a new variable where you transform time. It's not necessary to do that, but that's what you usually see in the literature. Yeah, so the Laplace is usually used for time transformation, and the Fourier transformation is usually used for space transformation. Then it turns out that in this transformed domain, the problem is solvable. And that means that you will get a solution in omega t or in xs. But that are not the original variables that you have, because you started here with x and t. So you have to apply an inverse transform. That's usually the integration in the complex plane. Integration in the complex plane, or you use tables. Yeah? And nowadays in packages like Maple, Mathematica, Maxima, all those transforms are given over there. So if you give the function in omega and t, or in x and s, yeah, what they know, they transform it back for you. Yeah? And what you then find is your solution in the xe coordinates. And there are more transformations, Humble transformations, yeah? But essentially they are doing this. So they transform to a new problem with new variables, then you can solve the problem, and then you have to apply the inverse. Yeah? So it's a simple idea of the methods. Now about what we know. Well, let's have a look. Let's consider a finite interval of length 2L. Yeah, let's consider a finite interval of length 2L. And actually, I would like to solve problems on an infinite domain. Yeah, so I would later on let L tend to infinity. But let's assume that we have a bounded domain. And I'm going to derive that from the bounded domain. And I assume that on the domain my function f is defined. What do you know? Well, if you write down the Fourier series, then you know that this is your Fourier series. Yeah, some of you already know all those coefficients by heart. An is 1 over L, integral from minus L to L. Fx cosine n pi x over L dx. And the Bn values are 1 over L, integral from minus L to L. Fx sine n pi x over L. Dx. The first formula is valid for n is 1, 0, 1, etc. And this formula is valid for n is 1, etc. This is what you learned when you applied the method of separation of variables. Yeah? The Fourier series. This is what we call a Fourier series. Yeah, so if you did elementary methods for PDEs, separation of variables, you do this. And this is actually the convergence theorem of what we have for Fourier series. And fx plus and fx minus means the left and the right limit to the point x. Yeah? And if f is continuous, a continuous function at interval, then we just have here fx is equal to this sum. Yeah? Okay, this is what you know. What I would like to do is I would like to rewrite this Fourier series in a complex notation. Yeah, what you do is you replace the cosines and the sines by the formulas that you already know. Yeah, so let f be continuous for simplicity. Yeah, then I know that fx is a0 over 2 plus summation n is 1 to infinity, an, and then I use the complex notation, e to the power I n pi x over L plus e to the power minus I n pi x over L divided by 2 plus dn e to the power I n pi x over L minus e to the power minus I n pi x over L divided by 2i. Yeah, that's just a complex notation, and I continue with that. A0 over 2 plus a sum. And then I take together this and this exponential. So I will get a half an minus I bn e to the power I n pi x over L plus a half an plus I bn e to the power minus I n pi x over L. Yeah? And this summation runs from n is 1 to infinity. And then for this term, I'm going to replace the n by minus n. Yeah, that means that I get over here a minus, here minus, and here minus. And if I then look at my coefficient n minus n, Yeah, what is it changing? Nothing, because the cosine is still the same. So that gives me an. If I look at b minus n, that will give me minus bn, because I have a sign over there. So this coefficient actually then is replaced by an plus ibn. And I have the same here, an plus ibn. Yeah? So I can rewrite this as a sum from minus infinity to minus 1. And here I have still a sum from 1 to infinity. Yeah? And if I have a 0, yeah, then I just have here this integral. Yeah? And the bn then is 0. Yeah? If I take n as 0, and I now define Cn to be, what is it, a half an plus I bn, then I can call this C0 and I can call this Cn. Also this Cn. Yeah? That's the idea. What's then happening? Then my infinite series becomes the following. Fx is equal to the sum from n is minus infinity to infinity Cn e to the power minus I n pi x over L. That's a very short notation. Yeah? So in complex notation, I can rewrite my, what is it, infinite series. Yeah, I started with a rather long series in a very compact form, and I know with Cn is actually equal to 1 over 2L integral from minus L to L. And I can rewrite it much faster as an plus I bn. Yeah? And that's 1 over 2L integral from minus L to L fx times e to the power I n pi x over L dx. Yeah? Write down what an is, what bn is. Yeah? So if I add those two, multiply here with an I, I get the same integrals. Cosine plus I sine, and that's e to the power I n pi x over L. Do you agree? an plus I bn, so if I multiply this with I, and then add the 2, then I get the expression. Okay. Yeah? Agree? So I have a rather compact form for my Fourier series in a complex notation. Okay, so there's nothing new. And now the question is, what happens when L tends to infinity? Then in between brackets, just to give a motivation for what I'm going to do next. So in between brackets, if we consider this equation, which is an, let's say a heat equation, and if you're working on a bounded domain, what did you find if you applied separation of variables? Yeah, so bounded domain. You found always solutions of the form e to the power minus k n pi over L squared times t times sine n pi x over L, or cosine x. Yeah? You found those solutions. And you only found solutions for very particular values here in the frequencies and here. So this is a bounded domain. Now let's have a look at this problem. So if I have a heat equation on an unbounded domain, H is running from minus infinity to infinity. What kind of solutions can we expect to see? Well, you can immediately verify that you get solutions of the form minus k times omega squared t. And what do we take over there? Yeah. You find solutions like this. You can immediately see that, substitute that into the problem. So if I take the derivative with respect to time, I will get minus k omega squared times this exponential times this exponential. If I take the second order derivative, I will get on this side k times minus I omega squared times this exponential, and then you see that it satisfies. But it satisfies for all omega. Yeah? And if you compare the two problems, then you usually say that this has a discrete spectrum and this has a continuous spectrum. Yeah, all omega satisfying that, whereas here there are only special omegas. Yeah. Okay. If you have an unbounded domain, you can also give, of course, an initial condition. Let's say this. Yeah, we have an initial condition. How many solutions do I find here? Infinitely many. So if I write down the general solution, I can add up all the solutions that I found. Yeah, so at least one solution is a constant which depends on omega times e to the power minus k omega squared t times e to the power minus I omega x. And if you want to sum up over all omega, yeah, because here we found a sum of eigenfunctions. If we sum up all solutions here, and we have to sum up over all solutions, then we have to take an integral. Minus to this. So this is the general solution. Yeah, you agree? With c omega still an arbitrary function. So here I can write down that this is my general solution. Well, for t is equal to 0, that should be equal to f. So that means that the integral from minus infinity to plus infinity, c omega e to the power minus I omega x dx should be equal to fx. How can I determine c omega? Because if I know c omega, then I know my solution. And remember, in the discrete case, what did we have? We had a sum. And here we had a sum over all eigenvalues. So that was an times, or cn times, doesn't matter, e to the power minus k n pi over L squared t times the sine, for instance. Yeah, that was our general solution. And then we had some rules how to determine an with orthogonality. Yeah, so we could determine the coefficients. The question here is also, how can we determine this coefficient? And that's related to Fourier series. Yeah? So this is the motivation. And brackets. Yeah, and you see that I have here an integral from minus infinity to plus infinity. I have this, and I have function fx, and look what I have here. I have here fx with something with e to the power minus I n pi over Lx, still discrete, eh? And if L tends to infinity, yeah, well, then this becomes 0. And yeah, I have a similar integral here. What happens when L tends to infinity? Well, first of all, I define omega n. Omega n is equal to n pi over L. And if I look at delta omega, which is defined to be omega n plus 1 minus omega n, then that is equal to pi over L. Yeah, so if I look at two consecutive omega n's, frequencies, then the difference is pi over L. And if L tends to infinity, pi over L tends to 0. So delta omega tends to that becomes d omega. That's an infinitesimal small interval. Okay. Assuming still that f is continuous. Fx is equal to let's have a look again what I have over here. Fx is equal to this, with Cn given by this integral. And I will do this in a moment. Yeah, so first I write down what I have. That is a sum that is minus infinity to plus infinity. Cn, I will substitute Cn, that's 1 over 2L. Integral from minus L to L. F x bar e to the power I n pi x bar over L dx bar times e to the power minus I n pi x over L. And I use here an x bar because this is a constant and I don't want to have confusion with this x and that x over there. Yeah? Okay. I'm going to use this. So what's happening with this? Well, I would like to have here pi over L, because then I have d omega. Pi over L, so I get 1 over 2 pi. And I place here pi over L. Yeah, so I change the 1 over 2L, I change nothing. Yeah, 1 over 2L, 1 over 2 pi times pi over L. Then I'm working with the rest of the formula. Sum n is minus infinity to plus infinity. Then I will get an integral from minus L to L. And I will get f x bar e to the power I omega x dx times e to the power minus I n pi, I omega x times pi over, yeah, I changed nothing. I only did this, omega is n pi over L, and I know this. So here I have actually delta omega. I'm letting I'm letting L tend to infinity. Well, this becomes an integral from minus infinity to plus infinity. Yeah, but I define this to be omega as a continuous variable. Yeah, knowing that this is omega n. Yeah. Yeah, it doesn't matter here. This is delta omega, and I call this is actually an omega depending on n. So this is running. Yeah. So if you write it like this or this, doesn't matter. Or if I write it like this, yeah, then I understand what I mean. So implicitly it's depending on n. Yeah. What do I have? If L tends to infinity, this integral becomes an integral from minus infinity to plus infinity. Nothing changing here. This becomes, for L tending to infinity, d omega. And what is the summation becoming? That's becoming an integral. Yeah, because I sum here over all the delta omega, and that sum becomes, in the limit, an integral. Yeah? So what I get is 1 over 2 pi, integral from minus infinity to plus infinity, integral from minus infinity to plus infinity, fx e to the power I omega x bar dx bar times e to the power minus I omega x times d omega. And that's equal to fx. So that's a rather complicated way of saying that fx is equal to this. Yeah. But I see something nice. I see something here, an integral over f e to the power I omega, that will certainly give me a function of omega. So here I have a function of omega. So here I have a function of omega times e to the power I omega x d omega. Hey, that's something I recognized. I wipe it out, it was on this last line. Fx should be equal to the integral from minus infinity to plus infinity. C omega e to the power minus I omega x d omega. So I recognize, if I take this separately, as a function of omega times that e to the power minus I omega. So I see that the structure is coming back. And now the definition. So now you can just say, I'm a mathematician. Don't worry about this lousy thing that we here derived. Yeah, this is only motivation. If I go to the definition, I just define what the Fourier transform is, and you can recognize it in these formulas. That's a definition. Fourier transform of fx is defined to be the following. That's a function f depending on omega, and that is defined to be 1 over 2 pi, integral from minus infinity to plus infinity, fx e to the power I omega x dx. That's the definition. The inverse Fourier transform of f omega is defined by fx is f minus 1 of f omega, and that's defined to be the integral from minus infinity to plus infinity f omega e to the power minus I omega x d omega. So these are the definitions. And let's now look how those definitions are connected to what we found earlier. Look at this formula. Fx is equal to. If you look carefully in this formula, then you see that this in total is what I call my big F omega. Yeah, so the Fourier transform of Fx is F omega is 1 over 2 pi times this integral. And you see it in here. What is the inverse? The inverse is the integral from minus infinity to infinity of F omega times this d omega. Okay, you see that? Yeah, so if this is F omega, then I have here the integral from minus infinity to plus infinity. F omega e to the power minus I omega x. F omega e to the power minus d omega. So you see from our lousy derivation of the Fourier transform, of manipulating Fourier series, letting out to infinity, we come to the definition. And if you look in books, and especially in books where they use tables, then there are two versions. In some books they prefer to have a symmetric transformation. So you will see that in the transformation you will have over here 1 over the square root of 2 pi, and then also over here 1 over the square root of 2 pi. In this book it's defined in this way, like in 95% of the books. So in most books they use this definition. Be aware that there might be another definition, but you can always see it if you look in the book of tables. Then usually in the first line you will have the definitions of the Fourier transforms. Is this so far clear? Because this is purely a definition, nothing else. Yeah? And it's derived from what we earlier saw with Fourier series. There's a smart thing to remember. If you would like to have the formula for the inverse, then it starts here in this with a minus. E to the power minus I omega x. Yeah, and in the original one you have plus. Another interesting thing to see is that if you look here at your function f, this looks of course like a Fourier series. It only states that your function f is built up out of infinitely many cosines and sines. Yeah, cosine omega x and sine omega x. Yeah, to sum it over all omega. Yeah, this is a summation to sum it over all possible sines and cosines. And this looks like your Fourier coefficients. F omega is this integral. Yeah, fx times cosines and sines. That are your Fourier coefficients. Yeah, if you have those Fourier series. So you see nicely how all things are fitting. As a mathematician, you should now look at this and you should say, actually, well, this is a generalization of our Fourier series. So more or less I'm doing the same thing, only it's generalized. Yeah? So there's a structure behind it. Okay, now we're going to make a table. So we're going to compute a lot of functions fx or big F omega functions, and we are making a table, and we are doing it in such a way that all the functions that we are going to meet the coming days, yeah, I'm going to derive that for you. Yeah, so a number of exercises can be made if you wish. And the first example is the following. Before we make this observation, observe that the Fourier transform of fx plus the function gx, yeah, it's a linear integral. Yeah, so that's the Fourier transform of fx plus the Fourier transform of gx, and that's just f omega plus g omega. Yeah, so if I have a sum of functions and I take the Fourier transform, then I get the sum of the Fourier transforms because of the linearity of your integral. Yeah, so that's an observation. Okay, first example. Let's assume that somehow we found in our computations g omega as being e to the power minus alpha omega squared. And I wonder what is the function gx that belongs to that. And it will turn out that this function plays an important role if you want to solve problems for heat equations. Okay, what do we know? According to the definition, gx is equal to the integral from minus infinity to plus infinity, g omega e to the power minus I omega x d omega. So I have to compute this integral.
It's hot, huh?
Yeah, it's warm.
Outside is cooler.
Outside it's cooler. Yeah, this is okay, nice. So I want to compute this, and actually I would like to compute this integral. And what I'm going to show you is how in practice you can compute those integrals. Yeah, so there are some general ways to solve it. Yeah, some you might call it, some mathematicians call it tricks, but actually they're not tricks. There are clever solution methods. Yeah. But we're going to show you how you can do that in many, many ways. One way to find what actually gx is, if the g omega is this, yeah, so you solve somehow a problem and you found in the omega domain this function. Then the question is, what is in the original domain or g, or small gx? Well, one way to do it is you differentiate this function g with respect to x. And the only x dependence is here. What you then get is the following. You will get the integral from minus infinity to plus infinity e to the power minus alpha omega squared times minus I omega e to the power minus I omega x d omega. Yeah. Then take the omega behind this, because I would like to do integration by parts. And then I get a half, so I have to multiply with 2. And then I also introduce alpha, so I put an alpha over there, so I have also to divide by alpha. Yeah, that's what I would like to do. So in the first step, I write down this as the integral from minus infinity to plus infinity e to the power I to the minus sign omega x times minus I times what is it? E to the power minus alpha omega squared. So I have to divide by 2, I have to divide by alpha, and I get an additional minus sign. Yeah. So if I differentiate this again, then I will get minus alpha times 2 omega And if I then divide it by 2 alpha, then I just have to 7. Okay. Yeah? Is equal to.
But there should be some another omega.
No, I take the omega first behind, that's omega squared, per half. Yeah, that's the 2 over here. Then I put over here also an alpha, so I have to divide by alpha, and I have here an additional minus sign, because of the exponential that I take behind it. Yeah, so I get I minus I over 2 alpha, e to the power I omega x, e to the power minus alpha omega squared. In between omega is minus infinity to plus infinity. And then I will get minus I over 2 alpha, integral from minus infinity to plus infinity. And then I get e to the power minus alpha omega squared times I omega, no sorry, Ix. Ix times e to the power I omega x d omega with a minus sign. Yeah? This was I get. Okay, looking at the first term, these are just bounded functions, cosines and sines. And here I have e to the power minus alpha omega squared. Upper bound, lower bound will always give me 0. Yeah? So this will give me 0. And then I'm left with this expression. And that's equal to, well, take I before it. Then I will get minus I squared, so that becomes plus 1. I can take out the x because it's an integration with respect to omega. So I will get x over 2 alpha times, times that integral. And, yeah. I get this. Is that correct? No, I'm missing somewhere a minus sign. Yeah, you're right here. I should have a minus Ix. Yeah? So we get a minus over here. Yeah, thank you. And if you now look careful, then that integral that I'm having over there is again gx. Gx is equal to this integral. So I'm left with minus x over 2 alpha gx. So the first order derivative of g is equal to this. And this can readily be integrated. And that gives you gx is g0 times e to the power minus x squared over alpha. For alpha. You have to take the derivative of x squared, that's a half x squared, so that's 4 alpha. Okay. Then I would like to know what is G0. Well, G0 is equal to the integral from minus infinity to plus infinity of e to the power minus alpha omega squared d omega. You agree? x is 0. Can we compute this integral? If you did statistics, you remember the normal distribution, yeah, where you also had these integrals. Yeah. And then you found that that integral was equal to the square root of pi over something with alpha. This expression. Okay, I have here another blackboard. So I'm going to write down here fx. And I'm going to write down here f omega in the table. And if I use fx, then I see that I will have over here the square root of pi over alpha times e to the power minus x squared over 4 alpha. Yeah? I'm making a table here, that's convenient for us. And then in the f omega space, that will be e to the power minus alpha omega squared. Yeah? Okay, so the table is continuing. Okay, then in the table you can also write down, of course, if you find e to the power minus beta x squared, and that's related to that, then it's obvious that you will find over here 1 over square root of 4 pi beta times e to the power minus omega squared over 4 beta. Yeah, that's the same like taking a special value of alpha. Yeah? Okay. So this is the first part of our table. Let's continue with another example. Okay, let's consider another example. Well, we don't need the table yet, but yeah, we are going to make some exercises, then we will need it. Yeah, if I put down the table here, then I don't have so much space to write. What do we encounter further? We encounter, if we consider Green's functions, we encounter delta functions. So I would like to know, if I take the delta function over here, what is the function in the omega space? So I will compute f omega, by definition, that's 1 over 2 pi, integral from minus infinity to plus infinity, of fx e to the power I omega x dx. And in this case, I just have to substitute the delta function. So what's the outcome of this integral? Yeah, you all agree? So if I take the delta function over here, then I will get 1 over 2 pi e to the power I omega x0. So if you find in the omega domain sines and cosines, or if you find a sine function, for instance, then let's assume that you find sine omega x. Sine omega x, of course, is the sum of those two exponentials. 1 over 2i e to the power I omega x minus e to the power minus I omega x. Hey. So then you get delta function in the original domain. So if you find sine functions, yeah? Okay. Let's assume that I find in the omega domain the function 1. The next example. What is the function in the x space? So if I find in the omega domain the function f omega is 1, what is the function fx? Is that a difficult exercise? And if you look carefully, the solution is already in the table. Yeah, so if I find in the omega domain the function 1, what is in the original fx space my function fx? Delta x. Because if I take x0 is 0, then I get over here 1. So in the original space, 2 pi times delta x. Yeah? You see that? Okay. Then continue. What do we have? We have derivatives here. Next example is about derivatives. I would like to know what is the Fourier transform of derivative. So I put over here now in my table df dx. And I wonder what is the function in the omega space. Well, let's continue. Write down the definition. So I have to compute this integral. Well, I can do integration by parts. Take f behind the d sign, the df dx behind the d sign. So I will get 1 over 2 pi, and then I will get e to the power I omega x times fx. In between x is minus infinity and plus infinity. And then I will get minus 1 over 2 pi integral from minus infinity to plus infinity. And then I will get I omega times fx times e to the power I omega x dx. Yeah. Plus integration by parts, one step. At infinity, I always assume that f and all of its derivatives are 0. There is no energy at infinity. So that means that the upper and lower bound here will always give me 0. Yeah, this is a bounded function, this at infinity is always 0. So this integral will give me 0, or this term will give me 0, and then I'm left with this integral, and that's equal to minus I omega times 1 over 2 pi, integral from minus infinity to plus infinity, fx e to the power I omega x dx, and if I'm careful, then here I have the Fourier transform of f. So if I take the derivative, then I will find over here minus I omega times f omega. So the derivative will always give me the factor minus I omega. You agree? Usually I have second order derivatives in my problem. Think of the wave equation, think of the heat equation. So let's have a look what the second order derivative is doing. Second order derivative. Another example. I would like to know the Fourier transform of the second order derivative. Well, that's not so difficult. Write down the definition. And I get this. Again, integration by parts. It's 1 over 2 pi f dx I omega x. X is minus infinity to plus infinity minus minus I omega times 1 over 2 pi times the integral from minus infinity to plus infinity df dx to the power I omega x dx. So that's after one step. Yeah? Integrated once. Well, f and all its derivatives at infinity are 0. So this again will give me 0. And then if I look careful, then it's minus I omega times 1 over 2 pi df dx. Hey, that's the same example as I computed here. That's this integral. That's the first order derivative. And that was equal to minus I omega times f omega. That this was f omega. So this then becomes equal to minus I omega squared f omega. In general, if you look at the nth order derivative of a function f, then you will find minus I omega to the power n f omega. So in my table I can write down that the nth order derivative is equal to minus I omega to the power n times f omega. Yeah? Okay. And then an important theorem, or actually an important transformation. Here. Usually, if you go to apply the Fourier transform, then you will find your solution in a form which is always a product of two functions of omega. Yeah, think of the Laplace transform that those students that did already ODEs and Laplace transform methods. Also there, you usually found your solution as products of functions of the transformed variables. So this is an important transformation. Yeah, so if I put here in my table f omega times g omega, then I'm wondering what is the original function that is going to that, because this is what we will frequently encounter. Yeah? Okay. So I would like to know what is hx belonging to h omega. Okay, by definition, what's the definition? Is this correct?
Yeah.
Yeah? Like this. What I'm going to do? Well, I don't know so much. The only thing that I know, for instance, is that I know my g omega, that's by definition 1 over 2 pi, integral from minus infinity to plus infinity of gx times e to the power I omega x dx. Yeah? So let's substitute that into the problem. Or I can do it similarly for my f. Yeah, but let's take one of the two. So it changed nothing, I only substituted the definition of my function big G omega into the problem. And what I now will do is I will interchange the integration order. Yeah, so now I have dx bar d omega, and I will make of that d omega dx bar. So what do I get? I would like to have the dx bar at the end. Okay, what do I get? I will get over here a gx. Yeah. Then I will get over here an integral from minus infinity to plus infinity f omega e to the power minus I omega x minus x bar d omega. Yeah? I took those two together. Yeah, I changed nothing. You agree? So what I did in those steps was only fill in the definition and interchange the order of integration. But now we should look carefully. If I look at this integral, to what is this integral equal? This is equal to the f, the small f of f minus x bar. You agree? If I use the definition of the inverse transformation, then I have to compute the integral from minus infinity to plus infinity. F omega e to the power minus I omega x d omega. But now the x is not x, but it is x minus x bar. So I will get the function x. The function f of x minus x bar. So this integral is equal to 1 over 2 pi, integral from minus infinity to plus infinity, g x bar, f x minus x bar, d x bar. I know my small f, I know my small g, I can compute this and I have my function hx. So here I will find then I get as an answer 1 over 2 pi, integral from minus infinity to plus infinity, gx bar f x minus x bar d x bar. And that's what we call the convolution integral. Yeah, so this is called a convolution integral. And if I interchange f and g, then you get the same answer, of course. Yeah, so we can also write it down as fx bar gx minus x bar. Yeah, let's give you the same answer. Clear so far? Okay, let's have a small break for about 5 to 10 minutes. And then I'm going to treat for you a partial differential equation with initial conditions and with boundary conditions. And then we're going to use the table. So I will make one exercise after the break. And then after that you're going to make yourself some exercises using these tables. Yeah? So a very small break, because if you lecture for 1 hour, I need a break, but you also need a break. Yeah? So we continue within 10 minutes. That's about 10:15. Yeah? Okay.
sugar cane. Cannot find it in all.
It's very, very effective.
This is our portion of snow plow.
Probably not wrong. Yeah.
An example. An example applied to the partial differential equation on an infinite domain. I told you that for infinite domains we cannot apply the method of separation of variables. And at the end, when we constructed the solution for this problem, you could also nicely see from the solution that you cannot separate variables. Yeah, that's also an interesting thing to notice later. Yeah, so separation of variables is only applicable to bounded domains. Yeah. Okay. What do we have as a problem? A heat equation. So we want to know the heat, the temperature in an infinity long rod, and we give the initial temperature, Gx. And of course we assume that at infinity, plus or minus infinity, there's no energy. Yeah, so G and all its derivatives and U and all its derivatives tend to 0 if X tend to plus or minus infinity. I would like to solve this problem by using the Fourier transform method. And if I apply the Fourier transform method, I have a choice. I can take the X variable or the T variable. But in my transformations, I always have the transformation running from minus infinity to plus infinity. So I can only transform in this problem the X variable, if I would like to apply the Fourier transform. So I'm going to do that with respect to the X variable. So I define the Fourier transform of my function uxt with respect to the X variable, and that's by definition 1 over 2 pi integral from minus infinity to plus infinity uxt e to the power I omega x dx, and that will give me a new function u depending on omega and t. Yeah, you agree? That's by definition the Fourier transform. So then I'm going to transform my problem with respect to x. So I can transform my PDE and I can transform my initial condition. So let's do that. So I take the Fourier transform of ut, and that should be equal to the Fourier transform of k times uxx. Yeah, so I Fourier transform my PDE. I do on both sides of the equation, I do the same thing. I take an integral, divide by 2 pi. Okay. What is the Fourier transform of ut? Well, if you don't know it, write down the definition. 1 over 2 pi, integral from minus infinity to plus infinity, ut xt e to the power I omega x dx. It's an integration with respect to x, so the time derivative can be taken out. So this is the ddt of 1 over 2 pi integral from minus infinity to plus infinity uxt e to the power I omega x dx. Hey, in between brackets I have the ddt of the Fourier transform, and that's big U. So this is the time derivative ut omega t. Ah, that's nice. That should be equal to the Fourier transform of this. Well, that's of course equal to k times the Fourier transform of uxx and if I look at the Fourier transform of the second order derivative of u with respect to x, I can look in my table. if I have a function, I take the nth derivative, it's in between brackets minus I omega to the power n f omega. So I will get minus I omega squared, because I have the second derivative, times big U. So this will give me minus I omega squared U omega t. So my partial differential equation now becomes ut is equal to, and that is equal to minus omega squared u. Yeah? So my PDE becomes this PDE. At least that's much simpler, because, well, I start here from a second order PDE, and this now is a first order PDE, but it looks like an ODE. So I can treat it as an ODE, and the constants of integration will be depending on the variables to which I do not integrate. Yeah? So I can solve this easily. But before doing that, I also will Fourier transform my initial condition, which is ux0, which should be equal to the Fourier transform of, in this case, gx. That implies, well, I take the Fourier transform of this, so that gives me big, and the Fourier transform of gx is just big G omega. So now I have to solve the following problem. T is equal to minus omega squared u, and u omega 0 is equal to g omega. Yeah, you're completely right. I have here k and I lost it here. So I should put here k. And I put also over here k. And I also put over here k. Yeah.
Only scale if you want.
Yeah, just a simple time transformation. By simple time transformation, you can scale it away. Kittiana has a problem in her PhD studies where she has lots of parameters. And then try to scale it away. Yeah, that's the... Okay. We solve this problem. We can directly do this. Is that the correct answer for the PDE? So I solved the PDE. That looks like the first order ODE. So the UDT is equal to minus omega squared k times u. Is this the correct answer? Or not? Who think this is not the correct answer? The C should be yeah, you agree? Because you treat it as an ODE, then the solution of the ODE is a constant times that exponential. But then you forget that it's not actually an ODE, but it's a PDE. So the variables to which you're not integrating, those variables are actually in your, between brackets, your constant. Yeah? So this is the general solution of that PDE. You always can remember that because you have a PDE, and if the PDE is first order, you need to have in your solution an arbitrary function. If you have a second order PDE and you want to have the general solution, then you should have two functionally independent functions. Yeah. Okay. Now at t is equal to 0, your u should be equal to g. And then you can determine this arbitrary function C omega. So if you do that, substitute t is equal to 0, then you will find that u omega t is equal to g omega times e to the power minus omega squared times kt. Okay, so it's not so difficult to solve the problem in the omega t space. Yeah, you can do that quite simple. Yeah? This is difficult to solve. You don't know how to do that. After the transformation, yeah, you actually obtain more or less an ODE problem. You can solve it directly. So in the omega t plane, you have your solution. But now I would like not to know my solution in omega t plane, but I would like to know it in the xt plane. So I have to apply the inverse. And now I have to look. I told you already, usually we'll find our solutions as product of functions. G omega times another function, f omega. So we should somehow use the last formula. But then I have to know, of course, what are the original functions belonging to g omega? Well, that's simple, that's gx. And I have to know what's the function that belongs to f omega. That's that nasty exponential, e to the power minus omega squared kt. Look up in your table if we find such a function. Yeah, the first one. And what is alpha? Kt. Ah, so I get something here with kt. So if I look at f omega is e to the power minus kt omega squared, and g omega is just an arbitrary function, yeah. Then I know that to this function, if I take the inverse of g omega, I will get small gx, and related to this, if I take the inverse of f omega, then I will get back, well, the first line, the square root of pi divided by alpha, and alpha is kt, yeah? Times e to the power minus x squared divided by 4 kt. Okay? So then I use, to obtain uxt, I use the convolution integral. I use the convolution integral, and then I find that my ux is 1 over 2 pi. Integral from minus infinity to plus infinity. Gx bar, and then fx minus x bar, so I will get over here the square root of pi over kt times e to the power minus x bar, yeah, x bar squared over 4 kt dx bar. Yeah, make it a little bit nicer, square root of pi and pi over here. So I can write that as 1 over 4 pi kt, integral from minus infinity to plus infinity, e to the power minus x bar squared over 4 kt times gx dx, and I still can rewrite it in another form. in this form. From this solution, you can immediately see that you cannot separate variables. Why? Because in that exponential, you have e to the power minus x over 4 kt. So you get something in an exponential minus x squared over t. How do you separate that? Can you write it as a function of x times a function of t? Answer no. So separation of variables cannot be done. You have a very simple solution. It looks very simple. Yeah, you agree? Also, I wrote the form of this solution in a very nice way. Because if I now ask you what's the Green's function? What's the Green's function that belongs to this problem? Then you recognize over here the Green's function xt because I gave the initial conditions. Yeah, that's a Green's function. I can also do it in another way. Let's assume that gx is the delta function, let's say, in a certain point x is x0. Yeah? T is already 0 for the gx, because I take my initial conditions. What happens if I do this? If I take this special initial condition. So at the point x is x0, initially I give an initial impulse in my temperature, and all the rest is 0. And then I wonder what happens with the solution. What is my u? I have to put over here delta x bar minus x0. So I will get as a solution 1 over 4 pi kt times e to the power minus
X naught. X naught. X0.
You agree? And what happens with this solution? Well, the limit for t tending to 0 of u xt, of course, should be the delta function, because that's my initial condition. And what is the solution doing if you make a picture? At t is equal to 0, I give that initial impulse. The area around it should be 1. And then if time increases, what's happening? Well, the solution starts to do this. And if I wait longer, it's doing this. So the temperature drops and spreads out. And the area below the curve will always be 1. Yeah? Is this clear for everyone? How to do this? Okay, then I have a few exercises. And the first exercise that you can make is out of the book. And that's exercise 10.4 on 3. And I will write down 2 other ones. And those other ones I also will partly discuss tomorrow. But it's nice if you try already to solve it, and then tomorrow you will see how you should solve it. If you did not find the answer. And let's see where I have the exercise. Yeah. Exercise number 2. If you look at the second exercise, then you have of course to determine U. This problem, well, if I take here a function fx, then actually the problem is something like this. This is our domain. And you know how to solve this problem by means of Ring's functions. Yeah. Now you will ask to solve the problem by using the Fourier transform. Determine 2x by using the Fourier transform method. Yeah, it's nice to see if you can find a relationship. And another exercise, that's exercise number 3. And the last exercise, that's an exercise that looks much like the problem that I studied a moment ago. Yeah. But I did not have the boundary condition. Yeah. That's the only difference. Same differential equation, same initial condition. Only now, x is not running from minus infinity to plus infinity, but it's running for x positive. Then I have the Dirichlet condition. And now I wonder whether I could use the last example that I treated. So I got 1 over the square root of 4 pi kt integral from minus infinity to plus infinity gx times e to the power minus x bar squared divided by 4 kt d bar. The question is, can I use that formula to solve this problem? And then you should think also how we used in the past the formula of D'Alembert to solve problems on bounded domains or semi-infinite domains. Then we used reflections. And the boundary condition always told us that we have a reflection. The question is, how is the reflection here? Well, we have a Dirichlet, so that most likely will be an odd extension. Does it also follow from that? And what you should do is take the solution from the problem I just gave you. In that solution, gx is defined only for x positive, not for x negative. So you can define for negative x whatever you like, but it will be determined by your boundary condition. And then again it will turn out it should be odd extended. So then you can use the solution of an infinite domain to solve the problem of a semi-infinite domain. And then you don't have to do all those chapters where people are working on Fourier cosine transforms, Fourier sine transforms, because those are only applicable to Dirichlet or normal conditions. But in a lot of applications you have also other boundary conditions, and then those Fourier sine and Fourier cosine methods don't work, and this is much more efficient to do. And then you don't have to remember or to look at other difficult formulas. Yeah? So make it yourself more easy. Yeah? So that's the goal of this exercise. But try to make exercise 10.43 and then continue. Of course, you're now allowed to have some coffee, yeah, but then you know what exercise you're going to make. Tomorrow I will discuss this example and I also will discuss this example. And then we will continue tomorrow with problems for the heat equation in higher dimensions. Yeah, how you should do that. And then it turns out that Green's function that I showed you, 1 over the square root of 1 pi kt, and the exponential e to the power minus x squared over 4 kt is coming back and back over and over again. Yeah? And then you can solve problems on infinite domains in R2, R3. And the same thing we are going to do for the wave equation. Yeah. Okay, I will have a short break and then we make some exercises.